All right, recording is rolling. It is Tuesday, January 30. You guys have this page out, chapter 16, 17, 18, and 19 from your book. We're going to solve these puzzles today. We're going to do something a little bit different. So you guys go ahead and solve these along with me, or maybe stay a step ahead is probably always a good piece of advice. Show me your work at the end of class, and then I will put in your grade as you're walking out the door today. Okay? The rest of this week, I have projects lined up. We're just going to do a 3D perspective project tomorrow, and then Zoetrope Thursday, Friday in the week. I'll get you guys a take-home quiz by the end of the week too. You guys have that. That's it. Yeah. All right. So just certain puzzles we're going to focus on. So chapter 16, fundamentals of light. Let's focus on. We're going to do numbers 16 and 17. I'll mention number 56. We'll go through that story to you, but not on paper though. Okay. Chapter 17, reflection and mirrors. Let's do numbers 71, 66, and 75. Ooh, I see some ray diagrams. I see that the equation that lines with that. Try those out. Chapter 18, refraction lenses. We're going to do numbers 67 and 73. Okay. Chapter 19, interference and diffraction. Well, I'll just say this here. We won't watch it. We'll just touch the first two chapters. Okay? Guys got that? All right, so that's our game plan. All right, so back to chapter 16, fundamentals of light. Right, so skipping some of these, obviously. At least just want to mention the stories. Okay? So like number 57 involves like there's like a lamp and a light bulb, and they're trying to equally illuminate a paper. The main concept you have to navigate with this one is inverse square law. Right? So like how bright is some light? Right? That's some posters related to that. So if you want to tackle that, go ahead. Number 56. Also, I want to look at the story because it's a really interesting story. So Ole Romer, so I think it's, I want to say he was a Danish astronomer, I think, back in the 17th century, so like Isaac Newton time, found that the average increased delay and disappearance of Io from one orbit around Jupiter to the next is 13 seconds. Ooh, what's this about? Right? And then it goes through a series of questions. So here, let me show you guys. I'm going to draw what he was seeing as an astronomer back in, this was like the 17th century, right? Okay, so here's, let's say this is the sun. Right, here could be Earth. And way out here could be like Jupiter. Right. Now, my picture's here, guys, everybody look here? Look here? Right. So this picture is not quite to scale, but it'll get the idea across. So here's Earth going around the sun. Right. Here's maybe Jupiter going around the sun. Right. Guys, which planet travels faster? Like if you have this point, yeah, Earth. Earth goes like way faster. Right. Jupiter takes a long time. It goes a lot slower. Okay. But Jupiter, from the point of view of Earth, if you're back in the 17th century, you can see through the telescope 4 moons around Jupiter. One of them is a moon called Io. Right? So he's watching Io. Here's Io, the moon, right? Go around Jupiter. And what he notices is that it takes about like 42 point something hours to go around, right? But it's not consistent. Sometimes it speeds up a little bit. Sometimes it slows down a little bit. Right? And what he realizes is that it has to do with the relative motion of these planets. He's getting effectively an early version of a Doppler effect. Right? So at some point in Earth's orbit, Earth is over here, moving sort of towards the Jupiter Io system. 6 months later, Earth is over here, moving kind of away from the Jupiter Io system. Right? Here, guys, everybody, focus here. So let's do this acoustic example. Let's say that you were out by the sidewalk and here's like a car, and maybe you and the car have some kind of relative motion, right? Wouldn't it sound like this? Right? You'd hear a pitch shift. Right? So like an increase in frequency when you're headed towards and a decrease in frequency when you're headed away. Right? Right. Now this is not acoustic. This is with light. Right? But light's gonna follow a also subject to this Doppler shift. You can call it red shifting and blue shifting. Right? Except he's not really looking at the colors. He's watching like the frequency of Io go around Jupiter. Right? Now, your textbook does have equations that you can navigate. I was working these out over the summer and recently, and I think they might have a little bit of a typo here. I don't think this observed frequency compared to source frequency is exactly correct. right? So I was doing some Googling and also some math, and I think it's a more correct version right here. It's a little bit different. So we're going to use this one, right? Or I'm going to play out this one anyway, right? So there's some actual frequency that Io is going around Jupiter, right? It's like some frequency of orbits, right? Take its time period of 40 something hours, one over that, right? But there's an observed frequency that's a mismatch. Again, when Earth's headed towards Jupiter, the time period decreases by some number of seconds, headed away, it increases by some number of seconds. Take the reciprocal of that, you get mismatched frequency. And maybe what's headed sort of parallel to Jupiter, you get sort of the idea of a true frequency, somewhere between those two, right? Right. Well, if you can figure out like what is the speed of the Earth going around the sun, which is like way faster than Jupiter, so just maybe focus on the motion of Earth. Okay. And you can pretty well get that, because if you can kind of figure out, well, I can get a pretty good idea of what is the distance from Earth to the sun. That's like the orbital radius, right? So multiply by 2 pi, that gives you the circumference of Earth, orbital circumference. Okay? And guys, how much time does it take for Earth to go one round trip around the sun? 365 days, right? So divide circumference by time period, 365 days, that can give you the speed of the Earth, right? Right. Now, what's the velocity of Earth relative to Jupiter? Well, sometimes headed towards and sometimes away. So there's your plus or minus, right? Do you guys see where the story's leading up to? I'm leading up to something I haven't even told you guys yet. What do you think he was trying to figure out? He was trying to calculate what? What's the only variable I haven't mentioned in this whole equation yet? How about c, which represents the speed of light, right? Right. Yeah. So you kind of figure out this Doppler formula, and you could figure out what's the speed of the Earth and what's the mismatch in these frequencies of Io going around Jupiter, and realize that was just an optical effect. Right? It wasn't really changing its motion. It was just right? He could back calculate what is the speed of light. Right? Now let's see in your textbook here, what exactly did he figure out was the speed of light? Right. So here's the story setup. Right. Okay. It's similar to the picture I just drew. Right? This goes back to, I mentioned some years here. Here it is. Between 1668 and 1674. Oh yeah, Danish astronomer, this one. Okay, so over in Denmark. What did he find for speed of light? He calculated 2.2 times 10 to the 8 meters per second. Right? And nowadays we have a better value of like 3 times 10 to the 8 meters per second. Right? So we definitely got the order of magnitude right. In fact, you got it pretty close, right? 2.2 versus 3.0. Right? Yeah. So there you go. That was like the first fairly 3.0.
Okay, yeah. So it's just 3 times.
Yeah, 3 times 10 to the 8 meters per second. There you go, right there. Right, is sort of modern day known value of that. Right? Yeah, so that was like the first pretty accurate calculated value for speed of light right there. Right. All right, so there you go. There's that story. Right. So are you guys ready to start writing some stuff? Right, we're just gonna on paper do these two, number 16, 17. So 16, a hydrogen atom in a galaxy moving with the speed of, also I think that's a typo right there. Right. I want to mention that too. You guys see where it says 6 point something times 10 to the 16 meters per second?
Yeah.
Right. But do you guys know the speed of light here, 3 times 10 to the 8 meters per second, that's like a cosmic speed limit. You can't move through space faster than this value, right? Right. Now, I want to expand on the story a little bit too, that this concept is related to this red shifting. Actually, that's what this poster is showing, right? So Doppler effect for light, yeah, equations, blah, 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 right? But this really shows up if you're looking at distant galaxies, and almost all galaxies relative to the Earth are like this red shifted, right? So if you're looking at those spectral lines, I guess that poster over there with the spectral, do I have the spectral lines queued up here? Let me find it for the video. Where's my spectral lines poster? Here it is, right? So go to the laboratory. Here's the first 8 elements of the periodic table. Right? There's like certain wavelengths they'll emit or absorb. Right? Well, if you look at distant galaxies, they're all shifted a bit towards the red part of the spectrum, except for like Andromeda is shifted a bit towards the blue, right? Something like that. Right? Tells you about the relative motion of the galaxies. Right? Hubble figured out about 100 years ago that the fact these galaxies are redshifted, and the further away they are, the more redshifted they are, right? Tells you that the universe is expanding. So let's get our calls MW, Milky Way. Right? If you're looking at all these galaxies relative to us, right? That they're all moving away from each other pretty much, right? There's this universal expansion, right? And they're expanding in such a way that there's no center of the universe. It's kind of like space is expanding uniformly everywhere. Right? Maybe the center of the universe is kind of everywhere, right? Kind of thing, right? Right. So when you get two galaxies far enough away from each other, then they can be moving away from each other faster than light. It's sort of one of those weird exceptions to be light, right? But it's not because they're moving through space, right? Faster than light, that would violate laws of physics, right? But the space between them is expanding such that they're moving relative to each other faster than light, right? So that if there's light emitted from these two galaxies, say towards each other, and space expanding too fast, light might never even reach the other galaxy, and one galaxy would never even be observable compared to the other, right? We don't even know how big the universe is. It might be infinitely big, which would be kind of crazy, but there's a limit to the observable universe for that. Right? Anyway, so side story I want to mention there. We're going to call this 10 to the 6 meters per second, just to do the math, okay? 10 to the 6 meters per second. Right? So maybe like roughly 1/100th of the speed of light, right? Which I think would make more sense, right? Away from Earth emits a wavelength 4.86 times 10 to the negative 7 meters. I'm going to rewrite that as 486 nanometers, which is equivalent to. What wavelength of light would be observed on Earth from that hydrogen atom? And think about these spectral lines. They maybe show up in the lab as certain values, but then you look into space and they're a bit redshifted. You put two and two together and figure out these relative speeds. I'm sort of saying the problem backwards of how they're giving it to us. Right? So number 16. Okay. We're gonna use this Doppler shift right here. Actually, now this one I think the wavelength of your book did get right. Here's a little bit modified version of it. I'm gonna play off this one, off my poster. Right? You guys see my poster, hanging in the room, right? And refer to that if you want. So the observed wavelength is equal to the source wavelength multiplied by, okay? And then let's bring in a Doppler shift for light. Okay? I'm gonna do 1 plus or minus the relative speeds of the galaxies, right? So how fast does the galaxy move to us, right? Compared to speed of light. Here we go. Okay. Is that now? Huh? Oh, we're doing that one. Okay. Yeah, everything. Okay. All right, then right, they gave us some values, and what are we solving for? What wavelength of light would be observed on Earth? Right. So we're solving for observed wavelength. So there's no algebra in the setup; it's all arithmetic. We're just going to plug numbers in. So they told us the observed wavelength is 486 nanometers. That's this right here, 486 nanometers. Right, multiplied by, right? And then, right, I got a plus or minus. So I got to navigate that. Now that depends on, is the galaxy headed towards us or away from us? It's going to turn the speed into a velocity, right? So if this galaxy is moving away, it says away, right? Should I go plus or minus? How about this? Right, guys, let's say you stand by a sidewalk, a car goes by. Let's think about an auditory example. Something, right? When the car is headed away from you, do you perceive that as an increase in frequency or a decrease in frequency?
Decrease.
That's a decrease in frequency, right? And what's happening to the wavelength then?
It's getting longer.
It's getting longer. So it's a plus. It's got to be a plus, right? Right. So all these red shifting, which is most galaxies compared to us, yeah, we're going to do a plus. So you're going to do plus. And they've got, okay, here's where I'm going to treat this as a typo. So 6.55, we're just going to go 10 to the 6 meters per second. Right? And then for the speed of light, we'll go 3 times 10 to the 8. Okay. All right, calculator time. Go ahead. You guys got calculators on your desk. Trust along. See if you guys get the same answer I do. Get practice with the calculator. That times 1 plus 6.556 over 78. All right, see what we're going to get. All right. I'm getting a number on my screen telling me 496 points. Yeah. Right. Kind of round a little bit to 36 bigs. Yes, somewhere thereabouts. Yeah, there you go. All right, you guys getting about that? Nanometers. There you go. Okay. All right. Now, this is kind of backwards of how astronomy actually works, right? Like you don't know how fast these galaxies moving, therefore what should the wavelength be, right? really it's backwards. It's, well, you're looking, say, with the spectroscope or your telescopes, right, up in the night sky, you see these distorted wavelengths.
Hi, teachers, at this time, please release all ninth graders to the auditorium. Again, at this time, please release all ninth graders to the auditorium. If you are a ninth grade teacher, please accompany your class to the auditorium. Thank you.
And you can back calculate what is the relative velocity of the galaxy, which is exactly what's being asked in the next question. Right, you guys ready for number 17? Right. Let's take it. So now we're doing more like true astronomy and number 17. Right. Maybe what Hubble was doing back 100 years ago. Astronomer looking at the spectrum of a galaxy finds that, let's say an oxygen spectral line. Ooh, which I think barely made my poster here, right? Oxygen spectral line, right? Is 525 nanometers, but the laboratory value is 513 nanometers. Okay? So pause right there. Are we looking at an example of red shifting or blue shifting? Here's the lab value. Here's the observed value in the sky. Red shifting. Because the observed wavelength is longer than the laboratory value, which means it's stretched out. It's red shifted. That's close to the red. The red wavelengths are longer in the visible part of the spectrum. Okay. Calculate how fast the galaxy would be moving relative to Earth. Right. Oh, and then explain whether it's moving toward or away. Well, you guys just kind of told me that, right? Red shifting, it's going away from us. Okay. Right. So we got to figure out how fast away from us. So let's do the same setup. The observed wavelength is equal to the source wavelength multiplied by fraction. Whoops, I got, well, so one plus. I should have done that. 1 plus. Okay. I guess you could get common denominator, blah, blah, blah. And then v that we're solving for divided by c, the speed of light. Okay, something like that. Okay. So the observed wavelength is 525 nanometers. But in the laboratory, it's shown as 513 nanometers. Right? So probably actually, and I did like that. Right? Right? Times, make this look a little prettier, 1 plus, and b over c here. 3, that's what I meant. Okay, so more like that, right? So for b here. Oh, and then you know to do plus because kind of like the previous question, it's red shifted away from us. Right? All right, so see if you can stay a step ahead of me, beat me to the answer here. All right. I'm going to divide that down, subtract that, multiply that. Boom, boom, boom. So I'm seeing 3 algebra steps from here on. Right. That, divide by that. All right, boom. Okay. And subtract that equals, well, v over c. So v equals all this times c. Like that. Okay. So I'm getting my calculator. Something like that. Roughly 1/100th the speed of light. Yeah, that's a reasonable number. All right, it's working out. So here, yeah, run you guys through these algebra steps again. Okay. So we started with just same expression as last question, okay. And we're solving for this v. Right? How fast away is that galaxy moving? And away, I went ahead and choose the plus. Okay. Okay, so here's the observed versus actual wavelengths. First thing I did was divide the source wavelength over. Right. Next thing you do is subtract over this 1. Right. And the third algebra step is to cross multiply the speed of light. Boom. I'll go. Okay. Okay. All right. All right. So you guys ready for the next one? Next one. All right. It's notes right there. Chapter 17, Reflection and Mirrors. Oh, I see some ray diagrams wanting to be set up. I see some equations. We got law of reflection. We got, there's the equation that can tell us mathematically what the ray diagrams are doing. Right? Got magnification. Okay. You guys see M, and then do you guys see 3 lines here? It looks like an equal sign, but with 3 lines. Here, guys. What does that mean? What is the equal sign, but with 3 lines? What does that mean?
I don't know.
It means defined as. So magnification is defined as the ratio of height of the image compared to height of the object. Okay, so it's definition of magnification. Okay. Number 71, jeweler's mirror. A jeweler inspects a watch with a diameter of 3 centimeters. Ooh, let's try this out. Hey, I got a watch that has a diameter of 3 centimeters. Oh yeah, look at that. Yeah. Taking it to a jeweler. Fancy Casio. Placing it 8 centimeters in front of a concave mirror with a 12 centimeter focal length. Ooh, you know what that's like? Notice, okay, we got a concave mirror. Hey, that could be like a cosmetic mirror. It could be a concave mirror. And notice we're placing it inside the focal distance. Focal length 12 centimeters. We're placing it 8 centimeters away. All right. Hey, that's kind of like you put your face nearby a concave mirror. The purpose of this cosmetic mirror is to blow up your face. I think we're about to do that with this watch. So the question is, where will the image of the watch appear and what will be the diameter of that image? Okay? I want to solve this 2 different ways. Let's solve this with a ray diagram, and then we'll do an equation version. Let's see if we get the same thing. Right? So, all right. So last class I ran into a little bit of trouble. I didn't quite position my picture right. I'm going to shut this down to the bottom left of my my picture. It said 12 centimeter focal length. Let me try to shut this as far left as I can. It's got right there. Okay. So let's get a ground going. We're going to set up a ray diagram. Here could be the plane of the mirror, and here could be the focal point. Right. So focal point's right there. Right. Here's my mirror. My favorite mirror. Right. Okay. You guys got that? Okay. And then we're putting the watch face 8 centimeters from the surface. That's like right here. Okay. And they're saying it's 3 centimeters tall. So go ahead and measure 3 centimeters. You guys got rulers on your desk, so you guys see this too. Right. So there, that picture is exactly what was described in the setup. Isn't that true? Right. You guys good so far?
Oh.
Spin my mirror a little bit there.
That's
right. Yeah, we did one ray diagram that was similar to the setup last week. Okay, good so far? Now, I remember these ray diagrams, there's a bajillion rays bouncing all different ways, but I can follow 2 rays to figure out exactly where the image is going to be. Okay? So I'm going to take my ruler, just use this as a straight edge. Let's have 1 ray going parallel to the ground across the top of the watch face. Boom. Okay? And that's going to bounce boing straight through this focal point. Okay? And then if you're an observer on the side of the mirrored surface, on the side of the watch, you say, well, it looks like that ray came from back this way. So I'm going to go ahead and dash off, like extrapolate. It looks like it came from back this way. Something about that, right? Okay, here, we draw a little observer eyeball. Here's an observer. Right. Right. Okay. And then let's follow another ray. Let's go from the focal point to the top of the watch focal point. We'll connect that. And I'm going to take that all the way to the plane of the mirror, which is right about here-ish. No, let's extend that a little bit more. Okay. And then that's going to bounce off, boing, back parallel to the ground again. Okay, parallel to the ground, boing, that way right there. Seems pretty close. Right. And then again, like this observer says, well, it looks like that light ray came from like back here. Okay. Okay, so it's still a little off page, but not too bad. Right. It's pretty close. Okay. Maybe I can scoot this paper like this and say it looks like it's going to cross way back here. About hereabouts. Okay, I still missed a little bit, but pretty close. Okay, you guys got that? Right. If you made a ray diagram and it doesn't quite fit on the page, well, that's okay. So where would the image appear to be? Well, measuring from the plane of the mirror, which is what the equation would also tell us relative to. It looks like about, okay, again, it kind of goes off the edge even of that page, but about 20 something centimeters. You guys think about 20 centimeters so? Right? Just seeing for my ray diagram. Maybe a little bit more than that, maybe about 20 something centimeters. Okay. And what would the height of the watch be? I mean, the whole purpose of this is to blow up the image. Right? Here, we're gonna have a watch. This isn't quite the right place, but here's like the blown up watch right here, right? Boom. Okay. So what's the height of this? Well, pretty much what is this height right here? I'm measuring 9 centimeters. You guys see 9 centimeters? Okay. Okay. You guys ready to do the math and see how close it is? Okay. Check it out. Math time. So where will the image appear? So question A. Let's do 1 over the focal length equals 1 over distance object plus 1 over distance image. Okay? And we're trying to solve for the image given those other two values. The focal length they said was 12 centimeters. And the object, they said, let's put 8 centimeters in front of the mirror. Right? Those both positive values. They're both on the same side. Right? I bet the image has to show up as a negative number, this distance image, because it's on the opposite side. It's a virtual image. Okay? Right. So say I'm going to subtract over 1 over 8, and then take the reciprocal. So 1 over distance image is 1 over 12 minus 1 over 8. Okay. And then take the reciprocal. Right. I should do it, right? Calculator. 1 over 112 minus 1/8. Okay. Oh, no, before I hit enter, I'm going to make a prediction. Because according to my ray diagram, remember I said it was like about 20 something centimeters away on the opposite side, which would make negative. I wonder if I'm going to get negative 20 something centimeters. Right, you guys think negative 20 something? Okay. Moment of truth. As soon as I hit enter, it's going to solve this. All right, you guys ready? Enter. Hey, negative 24 centimeters. All right, that is pretty well in line with that ray diagram. Negative 24 centimeters. All right. You guys got that? All right.
Wait, how did you get the D from being under the 1?
Reciprocal. So it's doing 1 over.
Oh, okay. So 1 over.
Yeah, 1 over. There you go. Yeah. Alternatively, there is a special key on your calculator that'll do that too. It's right above the 7. So it's x to the minus 1. That'll take reciprocal. All right. Now there was a question B that says, what will be the diameter of the image? That's like, how big is this? Right? I mean, hopefully it's bigger than the watch. That's the whole purpose of this type mirror, right? To blow it big. Right? And my measurement with my ruler here is showing about 9 centimeters tall. 9 centimeters. Right? But what does the equation say? The equation got magnification is defined as the ratio of height image to height object, which is also equivalent to the ratio of distances, di over do, and they also throw in a negative sign. So let's try that version. So magnification defined as h image over h object, which is also equivalent to negative distance image over distance object. Right? We know 3 of those things, and we're trying to figure out what is the height of the image. Right? So height image divided by, now height of the object was given as 3 centimeters. That's the actual diameter of the watch. It's equal to negative. Now distance image, we just found out was negative 24 centimeters. And distance object, well, where was the watch placed in front of the mirror? That was 8 centimeters. Right? You see that setup? Where all those numbers are coming from? Right. And then, 2 negatives make a positive. So that's convenient. Get a positive value. So guys, what is 24 divided by 8? 3. What is 3 times 3? 9 centimeters. 9 centimeters. What did I say it was going to be? No, I said 9 centimeters. I get it right every time. You guys getting it right too? Yeah. You guys ready for the next one? 66. Find the image position and height for the object shown here. Okay, it's pretty kind of light, but I think you guys can see also a concave mirror. Do you guys see also a concave? Right. Okay, so kind of like what you said, but now the image is outside the focal distance. They actually put it in this weird position where it's not quite twice the focal length away, right? Which is a weird place to put it, and you guys will see why when you do this diagram. Okay, so, 66, right? Now, the distances, they like 31 centimeters is more than the width of the paper, so I'm not going to exactly do that, right? But I'm going to draw a picture that looks pretty close to scale with what they have, right? So get a baseline here. Let's get a mirror going right here. Okay. Go ahead and put a focal point somewhere. Focal point, right? And then less than twice as far out. Go ahead and put an image, right? Yeah, the image is not quite twice as far out. Okay, so that's okay. Kind of close to what we got, right? You guys got something pretty similar to on your own paper? Okay. Oh, I'm using a stick figure. Paul Hewitt likes candles. Your textbook uses arrows for objects. I'm not really a fan of arrows because I think it's easy to confuse with the actual rays. Right. I like stick figures. Right. So there you go. My stick figure. Right, let's do ray diagram. Right. This one's a little bit different than anything quite we did last week. Okay. You guys see why. Okay. So let's follow ray of light, go across the top of its head parallel to the ground. That's going to bounce boing straight through this focal point. Okay, so we're off to a good start. Everything's all fine and good, except that I'm out of ink. Guess grab another pink pen. Come on. Aha! Another pink pen. Okay. Then let's go from the top of his head through the focal point, and that's going to bounce off the boing back parallel to the ground. Okay, and here's where this gets kind of weird, and I'm not 100% sure how to interpret this. If you're really curious, maybe go Google this one. Okay? But you guys see where the image is going to be, right? Where those lines cross? It's actually back like behind the object. It's kind of weird. Okay. Now, how could you interpret this? Maybe you could interpret this like the image was projected onto a screen, and you want it to be in focus. Like that's where you would put the screen to be in focus, maybe something like that. And it's gonna be upside down, something like that. All right. Okay. And then if you run the equation, it'll tell you pretty much the same thing. So 1 over F is 1 over DI plus 1 over DO. Okay. All right, you guys get there? All right, number 75. 75. I got some room down here. 75. All right, so we're going to a convex mirror. So let's do baseline. Again, I'm going to draw just something pretty close to what they got. Convex mirror. Okay. And actually, I can copy down their values. They got the object is 8 centimeters away. Here's their object. And they got the focal point as 4 centimeters away on the other opposite side. It's like right there, focal point for convex mirror. Now, last week when we did the ray diagrams, you might remember we did 3 of these, but they all kind of came out to the same outcome. Okay? So if you're ever looking in the backside of a spoon, that's what this was, right? Reflection, backside of a spoon. Okay? There's kind of only one thing that can ever happen. Okay? What does it look like? Do you look right side up and really small? Do you guys think right side up really small? Right? Let's see if that's what this is showing to. And then my poster version, I think I just made pretty much one of these because no matter where you position the object, you get the same outcome. So ray parallel to the ground, top of his head, that's going to reflect boing up to the left in such a way that you can align your ruler, your straight edge, with that focal point. Boom. Right. And it looks like that ray light came back from that direction. Okay. You guys good so far? Just labeling some stuff. Okay. Right, then let's go from the top of his head straight toward the focal point. So suppose there's a ray of light head straight that way. Okay. That's going to bounce off a Boing back parallel to the ground. Or vice versa. If you start parallel to the ground here, it would bounce back off to the focal point, like the other one. Okay. And where those two lines cross, right here, bam, there is your image right there. There you go. So if you ever look at the backside of a spoon, it doesn't matter if you're holding it close to your face, far away, or doesn't matter. You'll always see kind of the same thing. You see a virtual image looks smaller than in real life. Okay. Or how about this? Do you guys ever building 6? You guys know the music building over there? Right? There's a hallway that has a turn in it, and they have one of these type mirrors up around the corner of the hallway. Right? So if you're, I guess, like you're in a big old tuba or something, it's kind of hard to see around. So, guys, there's somebody coming around the corner. Oh, well, you can know for sure because you got one of these mirrors. Right? If you ever look in that mirror, right, everybody looks kind of small. Kind of small. You can see a lot in that mirror. Right? Right. Chapter 18. It's ready for chapter 18. Refraction. So we got a couple of refraction questions. Number 67. A ray of light travels from the air to a liquid as shown in this figure. The angle of incidence is 30 degrees, angle of refraction 22 degrees. Use Snell's law to calculate what is the index of refraction of the liquid. And then question B is, well, what could that liquid possibly be? And they refer to some table with indices of refraction. So let's get it. So Snell's law is that we did a lab on this. You guys remember N1 sine theta 1 equals N2 sine theta 2? Right, you guys remember that? Right, there's Snell's law. Snell's law. Right, we did a lab on that last week. Right. And they explicitly typed the angles, so we know the angles. Right? They also told you that one side is air. Guys, what is the index of refraction of air? It's like 1.003, I think, but I'll just call it 1. Right? We also rounded last week. Okay? And that sine of, and now the angle on the side of the air is 30-degree angle. Gotta do that. Ooh. You recognize, guys, what is sine of 30 degrees? Half? 1/2? Right? So you don't even need to calculate for that if you didn't want. Okay? So it's equal to N2. What's the index of refraction of this mystery liquid that refracted into? Okay? And then sine of, well, we know it's a 22-degree angle, and that's going to let us figure out what that is. Okay? Do you guys see one algebra step? Just divide sine down of 22 degrees down. So N2 is whatever is sine of 30 degrees over sine of 22 degrees. Okay. Sine 30 over sine 22. Okay. Looking at 1.3347. Let's call it 1.33. Right. Okay. Or that as precise as we can get there. Okay. Right, some of you guys might already know the answer to the follow-up question. What liquid is that? Water. Oh yeah, you guys do remember. Okay. Now they're referring to. Here's the chapter on refraction. They're referring to this table here, 18.1. Zoom in and see. Okay. So there's a perfect vacuum is 1.0 exactly. Oh, maybe I told you guys so slightly wrong. Air is 1.0003. Right, so I missed a 0. I told you guys. Right? But basically 1. Right? Right, water 1.33. There you go. We're probably looking at water. Right?
Ethanol.
Yummy. There's some other ones. Right? Got different kinds of glass. It's about 1.5-ish. Right? Guys remember? Right? And then there you go. Different indices of refraction. Right. So question B, the answer is water. Water. Right, number 73. Here's the last one we're doing. Number 73. Swimming pool lights. A light source is located 2 meters below the surface of the swimming pool and 1.5 meters from the edge. Right, so there's a light at the bottom of the swimming pool. Okay. And the pool is filled to the top with water. At what angle does the light leave the surface? Yeah. And does this cause the light to appear to be deeper or shallower than it actually is? Okay. Okay, so let's get a picture going. 783. So we got here's the pool, the water. See, 2 meters down, I can just call this side 2 meters, and then 1.5 meters this way. Here's the light, right? 1.5 meters, right? And we've got this light ray headed straight towards the edge. And I think the edge is a good place to pick. If you're walking around up here, it's like this observer up here would see what, right? Now, you guys know the angles that we're measuring with respect to is relative to a normal line, right? Like if the surface of the water is pretty much parallel to the ground, then the normal line would be perpendicular. So I can put that normal line right here at the edge. Okay. I'll see if you guys get this right. Okay. Which direction does that light refract? Does that light refract closer to that normal line or further away from the normal line? In fact, it's going from water into air. This is water. This is air. Right? Let's say show of hands. So you guys have been following for the last week. Okay. 2 options. Either option A refracts this way close to that normal line, or option B refracts this way further away from the normal line. I'm going to say option A. Who says option A? Who says option B this way? Option B. Yeah, there you go. There you go. You guys got it. Okay. This angle. Oh, I meant to label this angle too. Angle on the side of the water. Okay. So it'll get closer to the dashed line if it's a higher index of refraction. Water index of refraction is like 1.33. Air is like 1.0. Right. So yeah, so it's going to deviate away from that normal line, maybe into this guy's eyes. Ah, my eyes. So this angle right here, theta air. Right? That's the first thing we're solving for, right? It's going to go like that. Let's use Snell's law and figure out what is that angle right there. Right? Mathematically, what we're solving for. So n1 sine theta 1 equals n2 sine theta 2. Water and air. Water, air. So 1.33 times sine. Oh. I forgot about this. Could you do inverse sine of, or sorry, inverse tan of that over that and get that angle? You could. I want to do a little trick. Right? So you could do it that way. That's fine. Okay. I want to do a little trick here. Who notices what kind of triangle this is? Is this a triangle? This is a what triangle? 3, 4, 5. Ah, you see a 3, 4, 5 proportion, right? Scale of everything by factor 2, right? So would this side be 2.5 meters, right? Scale proportionally, right? And then what is the sine of this angle? What is sine? Is that opposite of our hypotenuse? That over that? Is that 3/5? Right. So instead of sine angle and find the angle and blah blah, what you could do? I'm just gonna put in 3/5. 3/5 right here. Because that is what that is for that proportional triangle. So 3:5 ratio. Right. So it's equal to well, on the side of the air, this is 1.0, right? Then sine of theta on the side of the air. Right. So sorry, it's not super pretty there, but it's 3/5 is what that is. Okay. All right, so there's one more algebra step I got to do. I got to take the inverse sine of both sides. I write that. So theta on the side of the air is inverse sine, also called arc sine, 1.33 times 3/5, and then all divided by 1, whatever. So inverse sine, 1.33 times 3/5. Okay. And that's 53 degrees about. Right? Right. Now, the next question is, does this appear to make it look deep or shallow? Let me see, show of hands. How many guys think this observer right here thinks, oh man, that light is way deeper, is like super deep, and then he sticks his head in the water, not as much? Who says that? Who says, this guy says, oh, it looks like the light's like just like right below the surface. Yeah, because, right, you guys got it. If you extrapolate backwards, this guy says, well, it looks like it's coming from like this direction. He thinks the light is right here. He thinks it's like right beneath the surface, right? Then he dives down in the water. He's like, whoa, it's way down there. But where he's standing right here, he thinks it's right above the surface. So it appears to be shallow. Right, you guys got that? Okay. All right. So, you guys got all that written. I'm going to walk around class. I'm just going to check your work. As long as everybody has it, I'll put the points in. While I'm checking you guys' work, let me play you guys I came across this. All right, let's check out this new Newton experiment. You guys, check this out while I'm checking your work. Got it. All right. Got